welcome you in the lecture series of random processes, detection and estimation. It is the 15th lecture of this series. In the previous lecture, we have discussed about multiple hypothesis testing, composite hypothesis testing. In this lecture, we will discuss about detection of deterministic signal in white Gaussian noise. The outline of this lecture are introduction, then we will discuss about the matched filter and the property of matched filter, frequency domain interpretation of the matched filter as maximizer of signal to noise ratio, and then we will discuss the performance of the matched filter. And in the objective of this lecture, you will be able to explain how practically the detection of the deterministic signal is possible and what is the matched filter, and you will also be able to explain how the replica correlator or matched filter is used to detect the deterministic signal in white Gaussian noise. Now we'll start with the introduction. The problems of detection of known signal means the deterministic signal in presence of white Gaussian noise has the extensive use in different signal processing applications. Here deterministic means you know the PDF of the signal which is to be detected. We can also say that it is a parametric detection, and in this detection, this detection takes the form of a replica correlator or matched filter. Now we'll start about the matched filter. In detecting the non-deterministic signal in white Gaussian noise, we will use a Neyman-Pearson criteria, and let we have two hypotheses H0 xn is equal to omega n, means under hypothesis H0 you have xn is equal to omega n, means in the hypothesis H0 there is only noise present, and under hypothesis H1 xn observed sample will be Sn plus omega n, means signal in presence of white Gaussian noise. And here Sn is unknown deterministic signal, and omega n is white Gaussian noise with mean 0 and variance sigma square. And you know the NP detector decide H1 or H0 if the likelihood ratio means PDF under hypothesis H1 divided by PDF under hypothesis H0 greater than less than threshold value gamma, and where X is X0, X1 to Xn transpose or n samples. This is the matrix X, and the PDF under each hypothesis will be here. Under hypothesis H1, the PDF will be pi n0 to n minus 1, 1 by under 2 pi sigma is to the power minus xn minus sn whole square by 2 sigma square. And you can write it as 1 by 2 pi is to the power n by 2 into 1 by sigma is to the power n is to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus sn whole square. And the PDF under hypothesis H0, it will be 1 by 2 pi is to the power n by 2 into 1 by sigma is to the power n is to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn whole square. So now the likelihood ratio, it will be Px H1 divided by Px H0 greater than less than threshold value gamma. So here the likelihood ratio will be e is to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus sn whole square minus summation n0 to n minus 1 xn whole square. This is here, and it will be greater than less than gamma. So taking natural log both side, you will get the log likelihood ratio test will be log ELX is equal to 1 by 2 sigma square summation n0 to n minus 1 xn minus sn whole square minus summation n0 to n minus 1 xn whole square greater than less than log E gamma. And you can also write it as 1 by 2 sigma square summation n0 to n minus 1 x square n plus s square n minus 2xn Sn minus x square n greater than less than log e gamma. So after cancellation of this x square n, you will have 1 by sigma square summation n0 to n minus 1 xn Sn minus 1 by 2 sigma square summation n0 to n minus 1 s square n greater than less than log e gamma. Here this part is not a function of data, so I can write this in this right side. So you will have summation n0 to n minus 1 xn Sn greater than less than sigma square log e gamma plus 1 by 2 summation n0 to n minus 1 s square n. So this is the new threshold value gamma dash, and this is the test statistic. So the test statistic will be summation n0 to n minus 1 xn Sn greater than less than the threshold value gamma dash. Here the threshold is chosen to satisfy the probability of false alarm is equal to alpha for a given alpha. From this equation, the test statistic weights the received data sample xn according to the value of the signal Sn. More weights is received for the large signal samples, and the detector of this equation is referred to as correlator or replica correlator, because we correlate the received data with the replica of the signal. And the block diagram for replica correlator is given here, because the test statistic is summation n0 to n minus 1 xn Sn. So from here the data xn and signal Sn, so we'll take the summation of this xn and Sn, we'll get the test statistic, and we compare this test statistic with the threshold value gamma dash, and if the value of this is greater than gamma dash, then we will decide h1 hypothesis h1 is true. Otherwise, if this is less than gamma dash, then we will take the decision in favor of hypothesis h0. In another way, the test statistic Tx or replica correlator detector can be viewed as doing finite impulse response filtering on the data. So if xn is a input to the FIR filter with sample response hn, where n0 to n minus 1, then output yn will be equal to summation k0 to n minus 1 hn minus k xk, the convolution sum. If we consider the impulse response of the FIR filter to be the flipped around version of the signal to be detected, so hn will be equal to Sn minus 1 minus n, where small n is equal to 0 to n minus 1. Then the output yn will be summation k0 to n minus 1 Sn minus 1 minus k minus 1 xk. And now the output of FIR filter at time n is equal to capital N minus 1 is yn minus 1 equal to summation k0 to n minus 1 xk, sk and xk. So yn minus 1 will be equal to summation k0 to n minus 1 sk nk. So we decide h1 or h0 if the test statistic Tx equal to summation n0 to n minus 1 xn Sn greater than or less than threshold value gamma dash. So this implementation of the test statistic using NP detector is known as the matched filter, and the filter impulse response is matched to the signal here. And the block diagram of the matched filter, you can see here the xn, and you will have FIR filter hn, and you will have here the test statistic. Then it will be compared with the threshold value gamma dash and if it is greater than gamma dash, then we will decide in favor of H1, hypothesis H1, and if the test statistic is less than the threshold value, then we will decide in favor of H0. The matched filter impulse response is obtained by flipping the signal Sn about n is equal to 0 and shifting to right by n minus 1 cycle. Means you are taking some kind of, you can say, the convolution. Now we are coming to the properties of the matched filter. The first property is frequency domain interpretation of the matched filter. You know yn is equal to summation k0 to n h n minus k xk convolution sum. The matched filter may also be viewed as the frequency domain. So in frequency domain, yn will be integration minus 1 by 2 hf xf e to the power minus j 2 pi fn df, where hf and xf are the discrete Fourier transform of hn and xn. And you know hn is equal to Sn minus 1, means we have considered the impulse response of the filter is to be the flip around version of the signal to be detected. So in this case, in frequency domain, it is hf is equal to Fourier transform of Sn minus 1 minus n, and it can be written as conjugate sf e to the power minus j2 pi fn minus 1. Then the output yn will be minus 1 by 2 to 1 by 2 s conjugate f x f e to the power j2 pi fn minus n minus 1 df, and sampling the output at n is equal to n minus 1, then we will get yn minus 1 will be equal to integration minus 1 by 2 to 1 by 2 sf conjugate into xf df, and when the noise is absent, xf is equal to sf, means the observed data will be the signal. In this case, when there is no noise, then the matched filter output is just the signal energy here, and yn minus 1 is equal to some integration minus 1 by 2 to plus 1 by 2 x square f df, in this case the signal energy. Now the second property is the matched filter as maximizer of signal to noise ratio SNR. The another property of the matched filter is that it maximizes the SNR at the output of the FIR filter. To show this, we consider all detectors of the form of FIR filter, but with arbitrary impulse response Hn over 0 to n minus 1. If we define the output SNR as E square yn minus 1 H1 divided by variance yn minus 1 H0, means the whole square of the mean value under hypothesis H1 divided by the variance under hypothesis H0, and it will be summation n k0 to n minus 1 h n minus 1 minus k s k whole square upon e expected value summation k0 to n minus 1 h n minus k n minus 1 minus k omega k whole square, because the mean value is 0, so it will be the whole square of the, and let matrix X is the S naught S1 to Sn minus 1 transpose, matrix H is Hn minus 1 Hn minus 2 to H naught transpose, and W is the matrix of omega naught omega 1 to omega n minus 1 transpose. So then you can write the output SNR of the matched filter will be H transpose S whole square upon expected value of H transpose W whole square, and you can also write here as H transpose S whole square upon H transpose E W transpose H, and the value of this expected value of W transpose, it will be sigma square identity matrix I. Then I can write this is equal to H transpose S whole square upon H transpose sigma square I H. So you are having the output SNR eta, it will be equal to 1 by sigma square H transpose S whole square upon H transpose H. And from Cauchy-Schwarz inequalities, you have H transpose S whole square less than equal to H transpose H and S transpose S. So from this, if H is equal to CS, if C is some constant, so the output SNR will be less than equal to 1 by sigma square S transpose S, and the maximum output SNR attained when C is equal to 1. So here Hn minus 1 minus n is equal to Sn for n0 to n minus 1, which is a matched filter. And so the output maximum SNR will be S transpose S by sigma square, and S transpose S is the energy of the signal epsilon. So the maximum SNR is the energy of the signal divided by the variance of the noise epsilon by sigma square, and this is known as energy to noise ratio. And the performance of the matched filter detector would increase monotonically with the SNR. Now we will discuss about the performance of the matched filter. To determine the detection performance of the replica correlator or matched filter detection, we need to derive the expression for the probability of detection PD for the given value of probability of false alarm. So for the replica correlator or matched filter detector, we decide H1 or H0 if the test statistic at Tx, it will be equal to summation n0 to n minus 1 xn Sn greater than less than gamma dash. Under each hypothesis, the data sample Xn are Gaussian and the test statistic Tx is a linear combination of the Gaussian random variables. Tx is also a Gaussian. So now the expected value of the test statistic under hypothesis H0, it will be the expected value summation n0 to n minus 1 omega n Sn, and it will be equal to 0. And the mean value under the hypothesis H1, it will be the expected value summation n0 to n minus 1 Sn plus omega n Sn, and this is the energy of the signal. Now the variance of the test statistic under hypothesis H0, it will be equal to variance summation n0 to n minus 1 omega n Sn, and you can write it as summation n0 to n minus 1 variance omega n S square n. And the variance of the noise is sigma square, so it will be sigma square summation n0 to n minus 1 S square n, and this is the energy of the signal S square, this is the energy of the signal. So you can write this expression as sigma square epsilon, the energy of the signal. Here omega n's are uncorrelated. Similarly, the variance of the test statistic under hypothesis H1, it will be sigma square epsilon. Now the PDF of test statistic under hypothesis H0, it will have the normal random variable with mean 0 and variance sigma square epsilon, and under hypothesis H1 it will have the normal random variable or normal process with mean epsilon and variance sigma square epsilon. So these are the figure of the test statistic, the PDF under hypothesis H0 and PDF under hypothesis H1 with the mean value 0 and with the mean value epsilon. If you consider T dash x is equal to Tx by under root sigma square epsilon, then the test statistic, new test statistic will have the normal random variable with mean 0, variance 1 under hypothesis H0, and normal random process with mean under root epsilon by sigma square and variance 1 under hypothesis H1. Here the PDF retains the shape, their shape, but move apart further as epsilon by sigma square increases. So the variance is the same here in this condition. The shape will be remain, and both hypotheses will move apart from mean 0 to under root epsilon by sigma square, and this obviously increase the detection performance. As the PDF under both hypotheses are known, we can find the probability of false alarm, and it will be equal to the probability of the test statistic t dash x greater than gamma dash when hypothesis H0 is true. And it is a Q function gamma dash upon under root sigma square epsilon, and you can also write it as 1 minus cumulative distribution function gamma dash divided by under root sigma square epsilon, or in the complementary error function you can write this expression or probability of false alarm as 1 by 2 ERFC gamma dash by under root 2 sigma square epsilon, and the probability of detection will be the probability of test statistic greater than gamma dash when H1 is true. So it will be Q gamma dash minus epsilon divided by under root sigma square epsilon. So you can also write it as 1 minus pi gamma dash minus epsilon divided by sigma square under root sigma square epsilon, and you can also write in the complementary error function form as 1 by 2 ERFC gamma dash minus epsilon divided by under root 2 sigma square epsilon. And from this Q function probability of false alarm, you can find out the threshold value gamma dash. It will be equal to under root sigma square epsilon Q inverse probability of false alarm, and put the value of this gamma dash in the probability detection, and you will find the probability of detection will be Q under root sigma square epsilon Q inverse probability of false alarm divided by under root sigma square epsilon minus under root epsilon by sigma square, or you can write this as Q inverse probability of false alarm minus under root sigma under root epsilon by sigma square, or you can also write it as, because this is the SNR as you have previously seen in the previous slides, so it will be expressed as in the Q inverse probability of false alarm minus under root SNR. So the SNR increases, the argument of the Q will be decreases, and the probability of detection will increase. So if I sketch the curve between probability of detection and the energy to noise ratio, you can find this curve, and this the PF increasing in this side, and it is apparent from the curve that to improve the detection performance we can always increase the probability of false alarm and or increase the ENR, energy to noise ratio. The ENR is increased by increasing the signal energy epsilon is equal to NA square. So the ENR, energy to noise ratio epsilon by sigma square, will be increased by either increasing the signal level N or signal duration is N, number of samples if we increase for a DC signal. The shape of the signal does not affect the detection performance, since the input SNR is epsilon by sigma square, or it is equal to A square by sigma square. Using a meshed filter to process N samples, the performance improves to the SNR. It will be epsilon by sigma square, and here the signal energy will be N A square by sigma square. The improvement in SNR means SNR output divided by SNR at the input is the processing gain, and this processing gain is equal to 10 log 10 SNR at the output divided by SNR at the input, and it will be 10 log 10 n. The processing gain can be viewed as the advantage of making a decision based on the test statistic, which is an optimal combination of the data. The another way, the meshed filter test statistic has the PDF of the mean shifted Gaussian column. It means you are having the Gaussian process with mean mu1 variance sigma square versus the Gaussian PDF with mean mu2 variance sigma square. Variance is same but mean are different here. So the deflection coefficient is characterized by the expected value under hypothesis h1 minus expected value under hypothesis h0 divided by the variance under hypothesis h0. So it will be equal to sigma d square will be equal to epsilon by sigma square, because in this case under hypothesis h1 the expected value of test statistic, it will be sigma minus 0 whole square by the variance under hypothesis h0 means variance of the mean, so it will be sigma square epsilon, and it will be sigma by epsilon by sigma square, because the variance of the test statistic under hypothesis h0 is sigma square epsilon. This deflection coefficient is just SNR at the meshed filter output. Now let us take one example. There are two competing signals, S1n is equal to A and S2n is equal to A. 1 minus 1 is to the power n, where small n is from 0 to n minus 1, where A greater than 0. The two hypotheses in this case are h0 is equal in the corresponds to hypothesis h0 xn is equal to omega n, and corresponds to hypothesis h1 xn will be si n plus omega n. So this means under hypothesis h0 there is no signal, only noise is present here, and under hypothesis h1 the signal si is present with the noise, and si denotes either of the deterministic signal S1n or S0n, and omega n is the white Gaussian noise with mean 0 variance sigma square. Now we have to perform which one of the signal would give the better detection performance. So we know that in case of detection of the non-deterministic signal in white Gaussian noise with variance sigma square, the detection performance of NP detector is completely characterized by the SNR ratio, and the probability of detection in this case will be Q inverse probability of false alarm minus under root epsilon by sigma square. Sigma epsilon is the energy of the signal, and this part epsilon by sigma square is the SNR. So now we will find out the energy of the signal S1. The energy of the signal S1 epsilon 1, it is equal to n0 to n minus 1 S1 whole square. So it will be summation n0 to n minus 1 A square, and it will be equal to n A square, and the energy of the signal S0 n, it will be epsilon 2, and it is equal to n0 to n minus 1 S2 n whole square, and it will be equal to summation n0 to n minus 1 A square, and minus 1 is to the power 2n, and it will be n A square. So here you can see both the signals have the identical energy. They would give the identical detection performance under white Gaussian noise. So far we have discussed about the meshed filter and their properties. This was the 15th lecture of the lecture series of random processes detection and estimation. In the next lecture, we will discuss about the generalized meshed filter detector and its performance. Till then, thanks for listening to this lecture. Thank you.